Hi chemists, my name is Kim and today we are going to be talking about equilibrium and Le Chatelier's principle. This video is just going to be going over the basics. What is equilibrium? And a little bit of how to make some predictions about what effects a stress will have. But this video is not going to go into super detailed practice problems about the impact that changes in concentration, pressure, or temperature specifically will have. There will be future videos that will look at those specific examples. So the learning goals for this video are to define chemical equilibrium, to identify sources of stress to a chemical system that might cause the reestablishment of equilibrium, and when told whether a forward reaction or a reverse reaction will be favored by a stressor, predict how the concentration of the reactants and the products will change in order to reestablish equilibrium. In other words, explain Le Chatelier's principle and make predictions using it. Let's get to it.
Equilibrium means a state of rest or balance due to the equal action of opposing forces. We say that a chemical system is at equilibrium if it is a reversible reaction where both the forward and the reverse reaction are happening at the same rate. So let's say we have reactant A that is reacting in a reversible chemical reaction to form product B. Product B can then react to form reactant A if the reverse reaction occurs. We would call this chemical system at equilibrium when A becoming B and B becoming A are occurring at the same rate. Another way to phrase this would be the forward reaction and the reverse reaction are occurring at the same speed, or that A is turning into B at the same rate that B is turning back into A. It means that even though constantly some A is becoming B and some B is becoming A, so individual particles may be changing their form and chemically reacting, the overall concentration of A and the overall concentration of B should remain constant overall. Now, this is important. That does not mean that there has to be the same amount of the reactant as product of A as B at equilibrium. There can be different amounts of A and B at equilibrium. There can be different number of moles. There can be different concentrations from each other, as long as the rate of formation of A is equal to the rate of formation of B. That is really what equilibrium means. Let's look at an example.
Let's demonstrate the concept of equilibrium using amounts of water to represent our reactant and product. So in this example, I have less reactant to start with than I have product. Let's imagine, though, that this system is at equilibrium. So the forward reaction, which is going to be reactant becoming product, I'm moving reactant to product with a mini cup here, that reaction rate is going to be happening the same rate as product becoming reactant. So let's think about what that would look like if I were to have both of these reactions happening simultaneously, because that's the way equilibrium systems work. The forward reaction and the reverse reaction are happening at the same time. Notice, I'm going to continue, and because these reactions are happening at the same rate, the overall amount of reactant and product, or in chemistry terms, the overall concentration of reactant and product, is staying the same, or roughly the same. Might be spilling a little bit, but you can forgive me that small amount of human error there, right? So we can see that when a system is in equilibrium, it's not that there is not a forward reaction and a reverse reaction happening. And it's not that both reactions are occurring. And it's also not that there is necessarily the same amount or the same concentration of reactant as product. It's just that overall, the concentration of the reactant and the concentration of the product stay constant because both reactions are happening at the same rate.
So let's talk about Le Chatelier's principle. Le Chatelier's principle is named after a French chemist who studied chemical equilibrium, Henri Le Châtelier. His description of how a system responds to a stress and to equilibrium has become known as Le Châtelier's principle. When a chemical system that is at equilibrium is disturbed by a stress, so the chemical reaction is occurring, the forward reaction and the reverse reaction are happening at the same rate. So if you were an outsider observing the reaction, you might see reactants becoming products, products becoming reactants, but they would be doing so at the same rate, so the overall change would be nothing. The overall change in the relative concentrations of the two reactants and products would be nothing. When that chemical system at equilibrium is disturbed by a stress, the system will respond in order to relieve the stress and return to equilibrium. In order to do that, it will need to temporarily favor either the reverse or the forward reaction. So when a system at equilibrium is disturbed by an outside stress, something in the system changes. The rate of either the forward or reverse reaction will change to reestablish equilibrium. Some examples of stresses to a chemical system include changes in the concentration of the reactants or the products. So if you are keeping them in a stable volume, changing the amount of reactant or product, changes in the temperature of a system, and changes in the pressure of a system. These are three examples of stresses to a chemical system that are the most common in equilibrium problems. There will be future videos with examples of how to analyze the impacts of each of these types of stressors specifically. For now, we are just going to think about the concept that a change to an equilibrium position in every case will either favor the forward reaction or favor the reverse reaction. So if we think about a chemical reaction as a double arrow, arrow going forward, arrow going backward, if equilibrium is disrupted by a stress, either the forward reaction, left to right, or the reverse reaction, right to left, will become favored. So if the forward reaction becomes favored, this means reactants are going to start becoming products faster than those products are turning back into reactants because the forward reaction is moving faster. This means that as from the point that the forward reaction becomes favored, we are taking reactant and turning it into product. The concentration of the product will increase if the forward reaction is favored. That's the reaction that makes product. And the concentration of the reactant will decrease because the forward reaction is using up the reactant to make the product. If we have the opposite happen, if a reverse reaction, so going from right to left, going back, if a reverse reaction becomes favored due to a stress, product will turn back into reactant faster than reactant is becoming product. It's like the opposite of what was happening when the forward reaction was favored. This will cause the concentration of reactant to increase because the reverse reaction is making more reactant. It will cause the concentration of the product to decrease because the product is becoming reactant faster than the reactant is becoming product if the reverse reaction is favored. Let's return to our example with the water cups. We're starting off with a higher concentration of reactant than product, but suddenly a stress occurs and the forward reaction becomes favored. This means that the forward reaction will be occurring at a faster rate than the reverse reaction. This means that more reactant for every given moment of time is turning into product than product is turning into reactant. So over time, this will actually lead to the amount of reactant or the concentration of reactant decreasing and the concentration of product increasing as the forward reaction is favored. Let's look at the opposite scenario. Let's imagine the reverse reaction is favored instead of the forward reaction being favored. This means that product is going to become reactant faster than reactant is becoming product. Again, both reactions are still occurring, the forward reaction and the reverse reaction. But now, since the reverse reaction is favored, the reverse reaction is happening at a faster rate. The rate of formation of the reactants is going to be higher than the rate of formation of the products, as represented by the size of the water cups. This will lead to an increase in amount or concentration of the reactants, since that is what is being made from the reverse reaction, and a decrease in the concentration or the amount of the products. Here's a summary table to help you think about the effects of a stress. Remember, those brackets mean concentration. So if the forward reaction is being favored, reactant is becoming product faster, then the concentration of A will decrease while the concentration of B will increase. If the reverse reaction is favored, then product is becoming reactant faster than reactant is becoming product. The concentration of A will increase while the concentration of B will decrease. Let's take a look at a couple practice problems. First one, for a reaction system at equilibrium, Le Châtelier's principle can be used to predict the, is it activation energy for the system, types of bonds in the reactants, effect of a stress on the system, or polarity of the product molecules. So the correct answer here, pause the video if you haven't decided yet, is 3, the effect of a stress on the system. Le Châtelier's principle predicts which direction or which side of the reaction will be favored after a stress on the system is applied. For a chemical system at equilibrium, the concentrations of both the reactants and the products must decrease, increase, be constant, or be equal. I'm going to eliminate 1 and 2 pretty quickly. It's not decrease or increase, equilibrium, right? That tells me that it's either be constant or be equal. Now you might be tempted to say equal, equilibrium, but remember, the concentrations of the reactants and the products do not need to be equal to each other. What does need to be equal is the rate of formation of the reactants and the products. In other words, the rate of the forward and reverse reactions. This actually means that the concentration of both the reactants and the products must be constant, but they do not necessarily have to be equal at equilibrium. Think about how the water cups did not have to have the same amount of water in each cup to be at equilibrium. Which statement describes a reaction at equilibrium? 1. The mass of the products must equal the mass of the reactants. 2. The entropy of the reactants must equal the entropy of the products. 3. The rate of formation of the products must equal the rate of formation of the reactants. 4. The number of moles of the reactants must equal the number of moles of the products. I'm going to eliminate number 1 because that's talking about the law of conservation of mass, not equilibrium. I am going to eliminate number 2 because I don't remember learning at any point that entropy of reactants must equal entropy of products. I'm going to eliminate number 4 because the amount of reactants does not have to necessarily equal the amount of products, and number of moles represents an amount. The answer is number 3. It's that the forward reaction, in other words, the rate of formation of the products, must equal the rate of the reverse reaction, the rate of formation of the reactants. Finally, the balanced equation below represents the reaction between a 5-gram sample of zinc metal and a 0.5 molar solution of hydrochloric acid. The reaction takes place in an open test tube at 298 Kelvin and 1 atmosphere in a laboratory activity. Explain why this reaction will not reach equilibrium. The key word here was takes place in an open test tube. Since this reaction is occurring in an open test tube, hydrogen gas can always leave the system, so the reverse reaction will never occur. Notice there's only an arrow moving in one direction. There's not an reaction arrow moving in the reverse direction, because that H2 gas is going to always leave the system and not react with the ZnCl2. If no reverse reaction can occur, the system will not be able to reach equilibrium. In general, an open system cannot reach equilibrium if one of the products is a gas. Checking back in on our learning goals, you'll notice that we did not talk about specific results of individual stresses to a chemical system. That will be done in future videos. We'll look at the effect of changing the pressure of a system, the temperature of a system, or changing the concentration of a reactant or a product. So this is just the first in a series of videos about kinetics and equilibrium. Nice job today. Thanks for doing chemistry with me.